Welcome back, guys. We're carrying on our study in the series chapter. We're looking at infinite geometric progressions today. You know what a geometric progression looks like. We know what the sum formula is. The sum formula of a geometric progression is Sn is equal to A, your first term in the series, multiplied by 1 minus r to the power of n, and that's all going to be over 1 minus r, so long as r is, the modulus of r is less than 1. So you could have anywhere between minus 1, not including minus 1, up to 1. So fraction values that are positive and negative. And so as n gets larger and larger, r to the power of n gets smaller and smaller. So that means that as n approaches infinity, Rn is going to approach 0. So you can imagine it as we get a big value for n. For example, let's say, why don't we say, let's say n, oh, whoops, I'd better turn the highlighter off. Let's say if n is equal to 99 and let's say r is equal to 0.5. Now if you go 0.5 to the power of 99, well, what do we get? 0.5 to the power of 99. Look, it's a very small number. I've got 1.58 times 10 to the power of negative 30. So you see, as the n value gets greater and greater, you're going to get that Rn, r to the power of n, is going to become closer and closer to 0. Okay, so long as the r value, the modulus of the r value is less than 1. Okay, if it's over 1, it's a different story. Now, if that's the case, then what happens is we can pretty much ignore it, and we can call it a 0 because it gets closer and closer to 0. So as we approach infinity, or the sum of infinity, we're going to get this formula here, a times 1 minus 0, which is just going to be a, all over 1 minus r, and that gives us the formula for the sum of an infinite series, which is a over 1 minus r, provided that the modulus of r is less than 1. Okay, let's do 3 questions. Number 1, the first 4 terms of a geometric progression are as follows, and we've got to find the sum to infinity. So I've got 3 minus 1, 1/3, minus 1/9. Okay, so I can see that I am timesing each time by minus 1/3. If you're not sure how to do that, you can just simply go minus 1 divided by 3. Right? Oh, that's minus 1/3. And then you just test and see that it works for all the others, which it does, of course. Okay, so the sum to infinity in this case is going to be a, which is 3, over 1 minus 1/3, because my r value is this bit here. So I've got 3 over that. Now, what do I get? Well, I've got 3 divided by 4 over 3, which gives me 9/4 is my sum to infinity. Okay, so let's take a look at number 2 now. We know the sum to infinity is 92, and we know the ratio is 3/4. So I can just set up my formula over here and put in what I know. Now I want to find this a business here. 1 take away 3/4 is 1/4. So I've got 92 is equal to a over 1/4. And I times both sides by 1/4, which is 46 there, 23. Yep, 23. And I will get a is 23. My final question for the day, number 7. The nth term of a geometric series is minus 1 to the power of n, 2 to the power of n. Find the first 3 terms. Well, we just insert n is 1, n is 2, n is 3. So, first part, first 3 terms. Well, if n is 1, what have I got? Minus 1 to the power of 1 is minus 1 times 2 to the power of, so I should have minus 2. Now I'm going to chuck in n is 2. So that minus 1 squared is 1, and 2 squared is 4, so that's my next term. And my next term is going to be when I'm put n as 3 in there. So I'm going to get negative 1 times 8. So I should have negative 8. And you can see that our value in this case is minus 2. Now, that takes me to part B. Explain why this geometric progression does not have a sum to infinity. Because for it to have a sum to infinity, r has to be, or the modulus of r has to be less than 1. But in this case, we have the modulus of r is greater than 1. Therefore, no sum to infinity. And that's as simple as that. Okay, my suggestion is you try the other questions in the exercise, have a go at them, let me know if you get stuck, happy to help. Alright guys, hopefully this is the last lesson in lockdown. I'm recording this on Monday the 11th, so I haven't heard Prime Minister Jacinda's announcement. Let's hope that we can be back together on Monday and Tuesday. God bless you guys. See ya.